Data is a collection of variables. It usually has the variable name in the first row and the values that that particular variable is acquiring for various cases in the following rows. So we, data consists of variables, and variables are those that acquire varying values for different units in the population. Now, this is an example of data where the first row is containing variable names like ID, name, age, number of fingers, sex, urine, sugar 1 plus 2 plus, and height and weight. These are the identification numbers of the population, case 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. And these cells will acquire the value for case number 1, value of name for case number 1, value of age for case number 1. So these are the value cells or the measurement cells. Now, if you look at name, it is a unique variable in the sense that name of 1 and 2 and 3 will be unique to 1, 2 and 3. Age is a continuous numeric variable. For example, the age can be 3.5 years or 6.7 years. It is continuous because it allows decimals, it allows fractions, and it is basically number. And all rules of numbers, addition, subtraction, multiplication, division, apply to the numeric continuous variables. But number of fingers cannot be cannot have fractions. You can not have 5.7 fingers. It can be either 5 or 6. So such numeric variables are called as numeric discrete. Then sex is a variable which is like name, like male or female. Okay. So male and female cannot be added or subtracted or multiplied or divided. So these are called as categorical variables. They define the category to which the person belongs. Then urine, sugar, 0, 1 plus 2 plus 3 plus is called as ordinal variable because this suggests an order. 2 plus is more than 1 plus. 3 plus is more than 2 plus. So this suggests an order. It has more information. And finally, you have the ratio variables. For example, if I say that 70% of 2021 batch will pass in Prasad Institute of Medical Sciences, 70%, 70 out of 100, numerator and denominator. So 70% will pass this year, then 70% should pass the next year, given all conditions are the same. Now this can be generalized to other populations other in time and other in place. For example, we say that if 70% is the result in PIMS, 70% should be the result in Era Medical College. So they are generalizable. Ratio variables are generalizable to other populations at other places and other times. That's why ratio variables are very important because they are generalizable, externally valid on other similar populations. So here is how you summarize the numbers or the values given in the columns against the population. For example, age column. So this is called as a frequency histogram of a frequency graph. Y-axis has frequency and x-axis has values. For example, age 1, 2, 3, 4, 5, 6, 7, 8, increasing values on the x-axis, and number of cases that had 5 years. For example, this may be 10 cases are of 5 years of age. So this x-axis shows you the frequency and this shows you the values in the column. This is called as a frequency histogram. Normally, there is a central tendency to this distribution, frequency distribution, and that central tendency can be mean, median, or mode. Mean is sum of all the values divided by number of all the values. Median is that value above which there are 50% of persons and below which there are 50% of persons. And mode is that value, like here 5 is that value which has the highest frequency. So these are the three measures of central tendency: mean, median, and mode. Then the other thing that you must know about the numeric distribution is that the values are dispersed around this central tendency, and that is called as dispersion. So one measure is range from this value lowest to highest. The second is called as interquartile range. That means 25% values are below the lower limits of the interquartile range and 25% of values are above the highest value of interquartile range. So interquartile range is from 25% to 75%. Okay. Then there is something which is called a standard deviation. Now the standard deviation is the mean of the deviation from the central tendency. Mean of all the values that are below, how much they deviated they are, and mean of all the deviations that are above. So that is called a standard deviation. It is usually denoted like plus minus 1 standard deviation, which usually has 68% of the values within that interval, plus minus 2 standard deviation, which has got 95% of the values within that interval, and plus minus 3 standard deviation across the central tendency, which has 99% of the values across that in that interval. So that is what we wanted to show you in this slide. So here you talk of the various types of curves. These two are normal curves where you see that the fall of frequency across the central tendency is symmetrical. And here you see that the fall on the right side is slower as compared to the left side. So these curves are called as skewed and these curves are called as normal curves. Now the normal curves are of two types. One is peaked, when the frequency for the central tendency is very high as compared to frequency for the other values. And here it is called as flat when the frequency for the central tendency is low as compared to other frequencies. So flat or peaked curves is what you see. It will be much more easier to see a difference between two peaked curves as compared to two flat curves, and you would get a peaked curve when the sample size is more and a flat curve when the sample size is less, because as the sample size increases, the values will fall near the central tendency and therefore the frequency of the central tendency will be much higher as compared to values away from the central tendency. Now, so the normal curve can be peaked or flat. This is called as kurtosis. Kurtosis is the ratio between the base of the curve and the frequency of the central tendency. and its normal value is base upon height, normal value is 2 upon 1. But of course, if the curve is flat or peaked, this kurtosis value will change. The skewed curve, the skewness is measured on the right or the left side by multiplying the difference between mean and median by 3 and dividing it by standard deviation. So that is the measure of skewness. Now we'll revise that there are two measures by which the numeric variables can be summarized. One is central tendency, mean, median, and mode, and the other is dispersion, where the values can be range, standard deviation, interquartile range, and confidence intervals. And confidence intervals are related to standard deviation. One standard deviation is equal to 68% confidence interval, two standard deviation to 95%, and three standard deviation to 99%. Let us show you an example of a skewed distribution and a normal distribution. So we open the Excel file here and we open a workbook, and here we say 1, 2, 3, 4, 5, 6, 7, 6, 7, and we go back 6, 5, 4, 3, 2, 1. Now this is symmetrical. It is sloping symmetrically on the two sides. Then let us say 1, 2, 3, 4, 5, 9, 11, 12, 15, and then say 12, 11, 9, 5, 4, 4, 3, 2, 1. Now here you see that the central tendency is much higher, so there is likely to be peaked. Then let us give you values of a skewed distribution. 1, 2, 3, 4, 5, 6, 7, 7, 6, 6, 5, 5, 5, 4, 4, 3, 3, 2, 2, 1. Now let us draw a graph of these three. So we say we highlight this. We say insert. We say we want this type of graphs, statistical graph, and like this. Insert this graph, statistical graph, and we want to say a line diagram. So this you see will be inserted, and this is a line diagram. So there is one type. Central tendency going up to 7 and gradually the frequency decreasing on both sides. Now we'll try to show you a peaked distribution where the central tendency is very high in between. And we say insert, we say graph, We say more statistical diagrams and say line. And so here you see that these values are lower like this. So it's much higher than the base. So this is a peaked graph. All right, peaking. The third, we like to show you this, a skewed graph. And the skewed graph is that we'll say insert, we'll say graph, and we'll say more statistical graphs, line diagram, and this is a skewed graph. So here you see a skewed graph. Now this is what we want you to understand: a normal graph, a skewed graph, a peaked graph, and a flat graph. The peaked graph is that the central values are going up to 16. Okay, so this is what we want you to understand. Now we are comparing two distributions. For example, hypertensive patients on drug A or drug B, how much is the lowering in the diastolic blood pressure? So this is the frequency distribution of patients that are taking drug A, and this is the frequency distribution of patients that are taking drug B. You see that this is the area where the patients can belong to either group A or to group B. So this is called as the intersection area. And this intersection area, if divided by total area under the curve, is called as intersection probability. So this is the area of overlap, and if you divide it by total area under the curve, you get the intersection probability, normally also called p-value. So if p-value is say 0.23, then the chance of belonging to both populations will be 23% as compared to the total population. And that is a high chance, and therefore the two values are not significantly different. So one thing is, are the two values significantly different? The other thing is that if you subtract the central tendency of one from the central tendency of the other, you would get a magnitude of difference. What I want you to realize is that as the sample size increases, the values near the central tendency will become higher, the curves will become more peaked, and the intersection probability will decrease. So the next slide will show you the effect of sample size on significance or p-value. So here you see a small sample size, a flat curve, a large intersection probability, and a difference which is not significant, statistically not significant, a high p-value. And here you see peaked curves, intersection probability is low, and therefore sample size will make you say that the two values are statistically significant if you have a large sample size. And therefore it becomes important how to calculate sample size, and we'll teach you how to calculate sample size next. So here we are comparing two groups, A and B, and trying to find out how much is the lowering of the diastolic blood pressure. So we go to the EpiInfo, and we go to the stat calc, and we say that we have a cohort study where one group is treated by treatment A and the other by treatment B, and we are seeing the lowering of blood pressure. So we open this, we say that the p-value is 0.001. That means only 1 in 1,000 chance that the difference that we see is significant. Then we say that our chance that we have wrongly diagnosed, we have correctly diagnosed the difference is 20%. That is the power of the study. We want the sample size to be very powerful. We say that the ratio between the exposed and unexposed, that means one is for treatment A and one is for treatment B, that means the ratio between A and B is 1. Then we say that the percentage outcome in the unexposed. For example, in A, let us say 25% will become normotensive, and in B, let us say 50% will become normotensive. Okay. Sorry, the risk ratio. That means, let us say that twice that number or even thrice that number will become, if the twice that number, that means 50% become normotensive in group B, then we'll say the difference is significant. And here we'll get the sample size 90 by this method, 94 by this method, and 108 by this method. So again, 20% is the power, 99.9% is the confidence interval. That means only 1 in 1,000 chance that the difference that we see is wrong. One case has treatment A to one case having treatment B. That means they are equally randomized to A or B. Now the percentage of benefit in the A group, let us say the conventional group is 25%. We want at least twice that benefit. That means 50% benefit in the experimental group, 50% difference in the experimental group, and this is the value for the sample size. I hope you have understood this method of computing sample size for studies where you are comparing two types of treatment. One group has treatment A, the other group has treatment B.